Hello, and in this video I want to describe the remarkable thing that happens when you take a block of p-doped semiconductor and a block of n-doped semiconductor and you put them together. I'll start this one with an animation. On the left hand side here we have some p-doped semiconductor with some vacant states in the valence band but practically no electrons in the conduction band. And on the right hand side, some n-doped semiconductor with some electrons in the bottom of the conduction band states, but the valence band effectively completely full. Now, what happens if I put the two blocks of semiconductor together and let them do their thing? That happens. If you missed it, that was it. An electron from the conduction band in the p-type material moved down into a vacant orbit in the top of the valence band in the p-type material. It doesn't have to move very far across the crystal to do that, and it can lose energy. And just like everything else, if something can move down to a lower energy state, it often will. You'll notice that the bands also moved. That's because a negative charge has just left the n-type material and arrived in the p-type material. So the n-type material now has a net positive charge. That means that it is attracting electrons into it, which means that the energy in these states has reduced. It's easier for an electron to arrive in these states. The reverse is true in the p-type material. That has just acquired a net negative charge due to the additional electron, so it is repelling other electrons, and you'd have to do more work to move an electron into one of these states. So these states have effectively gone up in energy. Now, what happens if you put an additional electric field across this junction? First of all, let's put an additional electric field in this direction, so the electrons are going to want to try and move in the other direction, and see what happens. Okay, well, the electrons in the conduction band here are able to move out of the crystal towards the source of the electric field, and there are some electrons that are able to come from the p-type material over here towards the junction, and they're going to fill up these remaining states. However, after you've got to this situation, no more current can flow. There are no electrons in the conduction band able to carry any current, and all of the available states in the valence band are now occupied, so none of these electrons can move. Net result, there's no current flowing. You'll notice that the band energies have changed too. This part of the crystal now has quite a large positive charge, since it's lost quite a few electrons, so it's very easy for electrons to arrive in these states, and the energies of these states has gone down. This part of the crystal now has quite a large negative charge and is repelling electrons, so the energy associated with these states has gone up. It's harder to get electrons into these states. Now, what happens if we try and put an electric field on in the other direction, so that the electrons are trying to move this way? Well, electrons can come in from the n-type material here into the bottom of the conduction band, travel along quite happily. The electrons can leave from the valence band here, leaving these vacant states behind them. These electrons, when they get close to the boundary, realize that there are vacant states underneath them, happily drop down in energy, and carry on out of the crystal. And we get quite an effective conductor. Electrons are flowing quite happily in this direction, which means the conventional current is quite happily flowing in the other direction. Remember that electrons are negatively charged, so if the electrons are moving from right to left, then the conventional current is going from left to right. We can represent what's happening in terms of these energy diagrams like this. Initially, when we put the two bits of semiconductor together and let them achieve an equilibrium, the electrons from this part of the n-type material will drop down into these vacant states in the p-type material. And they'll continue to do that until the Fermi level equalizes across the junction. Remember, the Fermi level is the average amount of energy required to add an electron. And if the average amount of energy was different on the two sides of the junction, then the average electron on this side could lose energy by moving across the junction. Equilibrium is achieved when that no longer happens, and the Fermi level is at the same point. Once you get into the body of the material, the Fermi level is just below the conduction band for the n-type material and just above the valence band for the p-type material. At this point, we have a slight positive charge on this side of the junction and a slight negative charge on this side of the junction, and that results in an electric field at the junction itself. It's caused by the electrons dropping down from the conduction layer of the n-type to the valence layer of the p-type across the junction. In a reverse biased p-n junction, so called because the external field that you add on, in this case by a battery cell being attached to this p-n component, is adding to that internal field built up in the junction, and it's resulting in a pattern of occupancy like this. The red dotted lines are the occupancy of the states calculated using the Fermi-Dirac distribution. And the reason why the current cannot flow, is electrons are trying to flow this direction, but in the p-type material, the only mobile electrons are at the top of the valence band in the p layer, so they're moving towards the junction, but in the n-type material, all those states are full, so they can't move. And they don't have enough energy to just jump up across the gap, enter the conduction band, and carry on out of the n-type material in the conduction band. Strictly speaking, that's not exactly accurate. The Fermi-Dirac distribution does suggest there will be a very small probability that these states up here will be occupied by electrons, so there can be a very, very small current flowing, but it's often negligible. With a forward biased p-n junction, the external field that you put on acts in the opposite direction from that internal field generated by the junction itself, and can overwhelm it so that the net electric field is actually in the other direction. In this case, the electrons are trying to flow this way, and that's much easier because they're flowing in from the n-type material over here towards the junction at the bottom of the conduction band. Then, at the junction, they have to drop down to the available states in the p-type material here at the top of the valence band, but it's very easy for electrons to drop down and lose energy. That's just like falling down. Much, much harder for an electron to suddenly gain the energy from somewhere and jump up. If I hold a pen in my hand, it's very easy for the pen to drop. It's very difficult for the pen to suddenly, by itself, just jump up. And that's the equivalent of what it's trying to do here. The electrons are falling off a step, going in this direction, but they're unable to climb up the same step when they try and go in the reverse direction. So we've built a component which can conduct electricity quite happily in one direction, but not the other. It's called a diode. And we'll be looking at them in a lot more detail in a few videos a bit later on.